Hello students, today we are going to discuss about the characteristics of solids. This is chapter 1 of solid state to steel class 12 and it is applicable for all the grades ICSC, CBSC and state boards. Okay, let us start. Thought, we can start with a very good thought. Success is achieved and maintained by those who try and keep trying. So, what is the meaning from this thought is, we should not lose hope. We should maintain the hope and try. Our try should not stop. There might be some failures in between. So our area is that we need to just clear that hurdles and reach to our goals. Okay, so fine. Let us start now. So learning objectives are, we will be able to clear all the characteristics of solids along with their structures, radius ratio and few numericals, imperfections in solids in regard to electronic, atomic and due to impurities. So this we have done in the previous video also. Here the types of solids means crystalline, amorphous. Under crystalline amorphous difference also there, basic difference is there. That is symmetrical arrangement is there, definite arrangement of atoms is there, and there is indefinite. And mostly we need to remember about the isotropy and anisotropy. Amorphous or isotropic means the same similar properties in different direction. Physical properties like refracting index, melting point, boiling point, that are same in different direction, but it is different in different direction in case of crystalline. So now under crystalline solids we are having atomic, molecular, ionic, covalent means covalent network, and metallic. So here we know the properties that atoms are composed, atomic solids are composed of atoms, molecular solids like carbon dioxide is molecule, ionic solid means NaCl, covalent network means SiO2 or diamond, metallic solid like copper. So we have to just see that what are the different properties. If you are talking about non-polar, that is soft and insulated of density and very low melting point. In examples, we should just see and we will understand more better. CCl4 non-polar, hydrogen, carbon dioxide, these are non-polar molecules. Similarly, if you are talking about polar, that will be almost similar, only HCl there, SO2. So somebody will ask, these are the gases, why are you talking about solids? Actually, you need to understand that any substance, when you decrease the temperature and increase the pressure, it will change its state. For example, I am taking carbon dioxide. Have you not thought of dry ice? So that is the meaning. Means any substance, whether it's a gas or liquid, when temperature is decreased and pressure is increased, that will be converted to solid. So we are talking of that solid after change in the pressure and temperature. Next is hydrogen bonded, as example ice. Okay, so some properties are there like melting point, boiling point. This we can once read, that is sufficient now. Now next topic is very important topic, that is radius ratio. Radius ratio is the ratio of radius of cation to radius of anion. Means to say that radius ratio is radius of cation by radius of anion. And you know that the radius of cation is normally smaller and then anion. So normally this ratio will lies between 0 to 1. It cannot exceed 1. So now depending upon the ratio, the different structures you will find. So if radius ratio is in between 0.225 to 0.414, so that arrangement is tetrahedral, and then if it is more than octahedral, and then it's 0.732 to 1 is cubic. So student may ask, sir, what about if less than 0.25? Yes, it can be possible, and it would be having coordination number, let us say less than 4. Less than 4 means it should be trigonal 3. Okay, so as the radius ratio increasing, the coordination number is increasing. That we have to keep in mind. And some examples also we should be remembering, that cesium chloride or calcium chloride, that undergo which is coordination number 8, and radius ratio is corresponding to 0.732. Okay, and cesium spelling always we should remember CaESium to be there. Okay, so here it is CSI written, but CaESium. Next thing is in regard to voids. Already voids we have discussed, only it is to just remember radius of tetrahedral void is equal to 0.2 to 5 of radius of atom, and radius of octahedral void is equal to 0.414 of radius of atom. So you can just see the range. You see the first part 0.25 to 0.414. This is tetrahedral. From this we can remember all these things. Now let us do a numerical on radius ratio. So this is the structure given. Cation radius is given and ion radius is given. You have to find this ratio, nothing else. So after the radius ratio, you can compare. If you find the radius ratio and compare that, you will find that how we can able to find the coordination number. For example, here in this case 0.759. Now you just see 0.759. What is the range? It is between this 0.73 to 1 cubic. So cubic structure 8. Okay, very simple numericals in this case. Now we are talking about NAC structure. Please see the atoms, red and green. The red is present at the corners and at the face, and green is present at where? On the edges. So if corner is there, what would be the contribution? 1 by 8, total 8, 1 by 8 into 8, 1. Yes. Face 1 by 2. How many faces? 6. 1 by 2 into 6. 3. 3 plus 1 by 8 into 8. 4. So yes, the red, whatever the red atoms were there, that is 4. And what about green? Green is 1 by 4 into 12. And 1 is in the center also. So 3 plus 1, 4. So it means to say that chloride ions present at the center of the edges and the center in the body center, and sodium is present at the corners and at the faces. Now here radius ratio is 0.25. So if you see the table, 0.5 to, so this will come under coordination number 6. So it means to say that each sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions. So this is the numerical, and the structure is FCC. So this is how we have to solve the calculations. Sodium is present at the body center as well as the edge center, and chloride ion present at the base and at the corners. So here we have calculated the number of atoms required is 4 and 4. So it means normally we are saying 4:4, 1:1 ratio. Okay, coordination number is 66 as the radius ratio. Now this was about iron solid. Now I am talking about covalent solid. That is also network also. If you talk about diamond, that's a network solid. And one atom solid is joined with 4 different atoms, forming tetrahedral ring. And in the graphite, what is there? One carbon. If you see, one carbon is linked with how many carbon? 3. So diamond is having sp3 hydrogen, graphite is having sp2. So where bond length will be less, whether sp3 or sp2? If you talk of ethane and ethene in +1, if you remember, where the bond length was less, when the double bond is multiplicity of the bond is coming, when unsaturation is coming, the bond length will decrease. Then you say, sir, bond length is decreasing, so bond energy will be more, so melting point of graphite should be more, but actually it is less. See, if you are talking about melting point of graphite is approximately that is less than the diamond. Diamond is having 3843 Kelvin melting point, but here it will be very less compared to that. And bond length, if you are talking of bond length of carbon bond length is 154 picometer as against to graphite of 141. So it is less, but then also strength is not there, right? See the layers. Between the hexagonal rings there are dotted lines. That dotted lines represent van der Waals forces. So these van der Waals forces are weak. So if van der Waals forces are weak, there may be space So space is there, the density will be more or less, volume will be more, density will be less. So more density of diamond, less density of grain. And the forces between the layers is very weak, 1 to 1. That's why graphite is slippery. Okay, and because one carbon atom is linked with the two other carbon atoms, so one it is sp2 hybridization. So it means one unhybridized orbital will be there to be that an electron will be there in that unhybridized orbital. So that electron is free to rotate. So graphite is good in rotation. Why? Because the presence of one unhybridized orbital which contains one electron. That electron can be moved here and there. So that is responsible for the conductivity in the graphite as compared to that. So these are electrons of carbon, graphite and diamond. So this way we are aware of that graphite and diamond structures. Now difference also you can do. So the geometry electrical, that is tetrahedral, and graphite is planar. Planar means sp2 hybridization, 120 degree angle. And soft and slippery, that also I told you why, and good conductor of XII, that's also I have explained about. Now next type of solids, metallic. Metallic is copper solid. So I would suggest you that you should always see the diagram from the book. It's very nicely it is shown there, and coordination of the gun is shown in the book. How it is shown that one center atom is surrounded by 6 atoms, and on the above layer then 3 are there, and then 3 below. So we can say that coordination of copper is 12, and it is having FCC stage. Now we are talking about the next topic, that is imperfections in solids. Imperfection solids, basically 3 different types we have to discuss. One is due to electronic, second is atomic, third is due to impurities. Electronic means, now you see that conduction of current is due to electrons. And if you remember that about the PCs and the chip set and all that, so that is made from semiconductors. So if you are talking of semiconductor, there is the flow of current that is due to two species that are called holes and electron. Hole is nothing but it is seed of electron, positive, empty, positive charge. It's a seed of electron is called hole. If an atom is there, electron is removed, balance left is hole. So the movement of hole and movement of electron are deciding the conduction of XII. And any imperfections to that is called electronic imperfections. Next is atomic. If atom is missing, if somewhere atom is missing, we are not talking of electrons, we are talking of atom is missing. And these defects are of 3 types: point, line and plane. So for example, point means one atom is removed, one line is removed, then there is line defect. One full-fledged plane is removed, like if you are having a room, full roof is gone. So these are comes under, after that we have discussed stoichiometry. Stoichiometry factor comes under vacancy and interstitial, that is one type, and Schottky triangle is the second type. And non-stoichiometric defect, matter excess due to vacancy, matter excess due to interstitial time, matter deficiency due to botanic vacancy. And next is impurity. Let us discuss one by one. Defect is what actually? Now you see in the diagram, V is there. V means vacancy. That is a defect. If you see I is interstitial. Extra atom is added. That is called defect. Interstitial. If for example you see this layer is totally not there. This layer is not there. One line is not there. So this is dislocated, and this is full line. And somewhere area would be there, or full line volume will be there. So that also is a defect. Okay. So we will discuss only basically point defects only today. So that only in our syllabus. Defect is what? Any departure from perfectly ordered arrangement of atoms in crystal. We have told already the atoms are arranged in a perfect order, regular order, that is called crystalline solid. But here we are talking of what is the defect? Defect coming why? Because when the temperature is increased at a 0 Kelvin or minus 273, you know, all the substance in this world will change into solid. Or before than that, 0 Kelvin will not attain. That is theoretical. All solids are having perfect arrangement of solids having state of lowest energy. Temperature decreasing, energy is lowest. Energy lowest stability. At high temperature, orderly arrangement is disturbed. If you increase the temperature, the arrangement is disturbed. That is called defect. It means defect occurs when the solid is subjected to some temperature pressure. Next is two types are there: stoichiometric and non-stoichiometric. Under stoichiometric, we are having again two types, non-ionic and ionic. What is stoichiometric? It is the ratio of number of positive and negative ions is not disturbed. When the ratio is not disturbed, for example, 5 cation and 5 anion, the ratio is not disturbed. Non-ionic solid, for example, vacancy. Vacancy means atoms are there and atom is removed from that. One positive is removed, one negative is removed. But in this non-ionic, only atom will be removed. One atom only we have to remove, non-positive negative. Under this interstitial, what is there? One atom is added. So when atom is added, so density will increase. When you are removing the atom, then density will decrease. Ionic solid, like for example, ion means both ions you have to remove, cation and anion. So density will decrease. Frankel defect, what is happening is the one anion, what is happening from that position will be removed from there, and in between the spaces it will come. That is called Frankel. So we are not removing anything, so density remains same. So let us explain in a new manner. So this is vacancy atom. Atom is missing. This is self-explanatory. Next is vacancy and interstitial. This is atom and this is non-ionic solid. Okay, now you see the vacancy will decrease, density will decrease in the vacancy defect and density will increase in case of interstitial. Next is ionic. Previously we discussed non-ionic. This is ionic. Schottky and Frankel. See the both cation and anion. One red is missing and one blue is missing. Red means Na plus, blue means Cl negative. So both are missing. So that is called ionic solid. And if what is happening? I am adding extra cation or not extra adding. Just what we are doing, displacement is there. From the previous position to the next position, only then density will not change. So this is the difference between Schottky and Frankel. It is given in the book, very important. This is, you should do very carefully. So basic thing is equal number of ions and ion missing, but here it is only the rearrangement of ion. It is an ion because it is in the ionic solid. So any ion will be missing from one side and take place the other and take place any other lattice sides. Density is decreased and there is no factor density. And it is in the highly ionic solids, like having cations and ions of same size. Okay, and here it is low coordination number and here is high coordination. Now just try yourself what should be the answer. Simple vacancy defect, interstitial, Frankel, Schottky. Density is changing or ionic. So you know simple vacancy and interstitial are which? Ionic or non-ionic? Frankel and Schottky. And which case the density is decreasing? Schottky. Schottky density is decreasing. So here I have to make changes. Actually, this is wrong. Third and fourth, it is changing. Density is Schottky density will decrease and Frankel remains. Okay, so we need to know here this is little bit of typographical accuracy. Okay. Next, non-stoichiometric defect. It are three types. Very important topics. So many questions are coming from this part. And previous also, Schottky and metal excess defect due to ionic vacancy, extenders. Metal excess due to interstitial cation, zinc oxide beating yellow and white and cold. This is question: why zinc oxide is yellow and white and cold? So we have to explain this metal excess defect in the interstitial cation. Metal deficiency defect due to cationic vacancy. Now I will tell you simple examples first, then we will take up. Let us take the example of sodium chloride. I am heating the sodium chloride crystal in the vapor of sodium. Sodium vapors are there, sodium I have heated, vapors are formed. That I am heating NaCl crystal in the vapors of sodium. What will happen? Cl negative will come out and combine with Na or Na plus. Sodium vapor means what? Gas state Na gas. So one electron will be lost. It will form Na plus. So it means to say that Cl negative is out from the crystal and it is removed. And now what about the vacancy? Now it is vacancy is there, no? Empty is there. So that electron is occupying that side. Which electron? I have told you that sodium chloride is heated in the vapors of sodium. Whether sodium will combine with Cl negative or Na plus will combine with Cl negative. Na plus. So that electron there is going to an ionic vacant side of chloride ion. So that defect, that point is called absenders, and this defect is metal excess defect. Okay, because we are removing the chloride ion, so this is metal excess. So we will see in the next slide. Next is metal excess defect due to interstitial cation. Now you just heat the zinc oxide. What do you get? You will get zinc 2 plus oxygen plus 2 electron. So oxygen will be out from the solid. What is left? Zinc 2 plus. Now zinc 2 plus is more, oxygen is less. So what happened? Metal excess, and that is having more conductivity. Okay, so that electrons, the excitation of electrons leads to movement from higher energy to lower energy. Once they will come back, they will emit the radiations which corresponding to vacuum. That's why showing color. Third is metal deficiency. You will understand. I will explain in the next slides all these. I am giving the introduction. Metal deficiency defect due to cation vacancy. Now this type of crystal defect is possible in case where the variable valency is there. Like for example, Fe early iron crystals are there, iron chloride let us say, or iron sulfide crystals are there. Iron will be removed, of which valency? 2 valency. How many removed? 3 were removed. So total 6 plus charge is missing. So if I add 2 Fe3 plus ions, so then also same only. So this is only happening in case of cation vacancies. C. These are the two cases. F center case was C. Sodium chloride we have taken the example. Cl negative is missing, and what takes the place of Cl negative? Electron. So anionic vacant sites are occupied by electrons that are called F senders. Anionic vacant sites are occupied by electrons. Metal excess defect due to anionic vacancy. Second is metal excess defect. As I told you, if you are heating zinc oxide, you will get zinc 2 plus 2 electron. So these 2 electrons are moving here and there, so it will conduct electricity. And moreover, now zinc 2 plus is extra. Okay, so metal excess due to extra cation. That A is representing the zinc 2 plus is there, B is less. Okay. Next is, this is F center. So F centers are responsible for color. Why? Because the electron, because once you are heating, the electron will jump to higher energy state and it will come to lower energy state after absorption of energy. So the energy release corresponds to violet color. For ACl, pink color for ACl, sodium chloride. So we know that Cl will put on the flame of sodium energy flame test. Okay, this is metal excess defect due to anionic vacancy. Next is F center. Anionic vacant sites are occupied by electron. See, this electron Cl negative is replaced by electron. It is responsible for color. Now earlier we discussed of metal deficiency defect. That is iron. Sodium is replaced by strontium, or iron 3 Fe2 plus is replaced by 2 Fe2 plus. So one vacancy will be generated here. So this will be responsible for the production of X. Now last type of defect is impurity defect. Impurity means there are 2 types of semiconductor. Previously we discussed electronic defect. Electronic defect means what? The defect due to presence of electrons. When you heat, the electron movement will take place and that will be responsible for the conduct. So that the semiconductors are called intrinsic semiconductors. That are not the defects. That simply we are saying that these solids are there. The defects. Defects means when you are heating, the movement will take place of electrons, or some dislocation will take place. So when you are adding some impurity, this intrinsic semiconductor changes to extrinsic, because intrinsic semiconductor is not having much conductivity. It's very poor conductivity. When to increase the conductivity, we are adding some dopant. So dopant is what? So dopant will increase the conductivity of this solid. So there are 2 types, P type and N type. So now current I told you that it's due to 2 species, holes and electrons. If holes are more than electrons, then it's called p-type semiconductor. And n-type, electrons are more, number of electrons are more than number of holes. This we as a concentration. Concentration of hole is greater than concentration of electron, that is p-type. Concentration of electrons greater than concentration of hole, that is called n-type. So now here, what makes p-type or n-type? Now we are having, let us say, group 14 element, silicon. When silicon is replaced by aluminum, now silicon having 4 valence electron and aluminum having 3, so which will be excess, holes or electrons? Holes, sir. So hole means p-type semiconductor. And if I am taking group 14 element, if I am taking silicon out and again substituting with phosphorus, then 5 valence electron is there, the phosphorus, and silicon having 4, so 1 electron is be excess, so the number of electrons will be greater than number of holes, then it will give me a what? N-type semiconductor. So doping. Introduction of defects by the addition of foreign substance in a crystal of a pure substance is called doping. Introduction of defects by the addition of foreign substance in the crystal of pure substance. Then what impurities you are adding to improve the conductivity of the solution is called doping. The process is called doping, and what you are adding is called dopant. And it of two types, p-type semiconductor and n-type. I already discussed that. If 14 is doped with 313, then it's called p-type, and if 14 is doped with 15, then n-type. Now let's recap. Radius ratio is more, coordination number is more, and radius ratio is ratio of cation by 9, and it tells us about the geometry of the solid also. Short-kin fragment effects are stoichiometric effect in ionic solid. We can say interstitial effects are stoichiometric effects in ionic solid. Stoichiometry means number of cation, number of ion, the ratio will be same. And matrix test, if you do due to an ionic vacancy, matrix test due to interstitial cation. Ionic vacancy is absent, same. Matrix test due to interstitial cation is that zinc oxide heating case. Metal deficiency due to ionic vacancies are that Fe2 plus changes with Fe3 plus, and doping is addition of impurities. So I would like to repeat the thought, that is, success is achieved and maintained by those who try and keep trying. So I would say to you that you should keep trying and you will get the success. Thank you very much.